Welcome to Math with Professor V. Here's your latest integral of the day. We have the indefinite integral of the square root of x squared plus 2x plus 2 over x squared plus 2x plus 1 dx. And I picked it because I want you guys to use this as an opportunity to test yourself, especially if you're someone who follows along with the playlist. It involves a few techniques that we've had to use in the past week's integral of the day solutions. So I thought it would be a nice opportunity for you guys to see if you can apply all of these techniques together and solve this problem on your own. So I recommend pause the video, try it on your own first. You should be ready to go. What we're gonna do is complete the square underneath the radical in the numerator, do a trig sub, and then the rest of it should be familiar from stuff we've been working on in the most recent videos. So underneath the radical, if you'll notice, we've got x squared plus 2x plus 2. I can factor that into x squared plus 2x plus 1, or rewrite it that way. That way I can have x squared plus 2x plus 1 grouped together. That's a perfect square trinomial. And then I have another plus 1 hanging out, which is perfect. We're going to do trig sub. And in this case, I want to let the entire variable quantity x plus 1 equal 1 tangent theta. And then that means dx would be secant squared theta d theta. Fab. So let's rewrite things before we do the trig sub. So we're ready to go. I have square root x plus 1 squared plus 1. The denominator is already a perfect square trinomial, x plus 1 squared dx. So then we'll come through. We have square root tan squared theta plus 1 over, the denominator is going to become tangent squared theta, yes. And then dx is simply secant squared theta d theta. Beautiful. Okay, tangent squared theta plus 1, that's secant squared theta. Then we take the square root, so then it's just going to become absolute value secant theta, but we don't need to worry about the absolute value because we've restricted where theta is. So all of this is secant theta. And then I've got secant squared theta hanging out here, which means in the numerator altogether now we have secant cubed theta. And then I have tan squared theta in the denominator d theta. Very good. Okay, I'm not noticing any beautiful, easy, clean u subs that I can do. I always go through the two options in my head. If I let u be secant theta, nope, there's no secant theta, tan theta in the numerator. If I let u be tan theta, du is secant squared, but I've got one too many in the numerator, and if I have an odd number of extras, I'm stuck. So nope, that's not working. Then the next thing my mind goes to is, okay, let's just rewrite everybody in terms of sines and cosines and then see if we can play around with it. So secant cubed theta, that's 1 over cosine cubed theta. And then tan squared theta in the denominator really is cotangent squared. So we've got cosine squared theta over sine squared theta d theta. Ooh, cosine squared cancels. Then I just have one cosine in the denominator. So this is 1 over cosine theta times 1 over sine squared theta d theta. Now hopefully here you had flashbacks to a couple integrals that we did earlier where we forced the u sub to happen by multiplying top and bottom by either sine theta or cosine theta. And in this particular case, we're going to multiply by cosine theta in the numerator and denominator. That way I can make the substitution to let u be sine theta. So watch what happens. In the numerator now I have cosine theta d theta. In the denominator, I've got cosine theta times cosine theta, which is cosine squared theta. I'm going to rewrite it as 1 minus sine squared theta. And then I still have another sine squared theta down here. This is perfect though, because now we can go ahead, let u be sine theta, not squared, just the function by itself. And then du is cosine theta d theta, which we made sure we had in the numerator. Perfect. So carrying on, we have du over 1 minus u squared times u squared. And yes, dun, 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 it's time for partial fraction decomposition. Okay, so partial fraction decomp time. And I think we've done this exact same function or super similar. 1 minus u squared factors into 1 minus u times 1 plus u. And then u squared, just leave it, but remember that's a repeated linear factor. So the decomposition will have the form a over 1 minus u plus b over 1 plus u plus c over u plus d over u squared. And then we're going to multiply everything through by the LCD. So 1 minus u, 1 plus u, and u squared. Good. So on the left, we've got 1 equals a times 1 plus u, u squared, plus b times 1 minus u, u squared, plus c times 1 minus u, 1 plus u, and a u, and then d times 1 minus u, 1 plus u. Okay, so let's start solving for a, b, c, and d. I'm going to substitute in different values of u to zero things out, starting with -1. So I'd have 1 on the left. This whole term's gone. I'd have b times 1 minus -1, so that's b times 2, and then times -1 squared, that's just 1. This would be 0. All of this is 0. All of this is 0. Anybody who has 1 plus u is 0. So then, bam, I know that b is 1/2 now. Great. Repeat. Let's let u equal +1. Then I have 1 equals a times +2. If u is 1, this is gone. 0, 0, 0. So then I know a is 1/2. Okay, next, let's let u equal 0. So 1 equals, this is gone, this is gone, this is gone. Then we have d times 1 times 1. So d is 1. And then we need to find c. And you're like, what do I plug in for u to zero everybody out? You don't. You just pick something nice to plug in for u. Since we already have b, a, and d, you just pick any old constant your heart desires. And then I'll also put 1/2 here, 1/2 here, and we'll find c. I went with 2. You can do whatever your heart desires, okay? Just don't pick something that'll make it too spicy. 1 equals, I know a is 1/2. 1 plus 2 is 3. 2 squared is 4. Plus b is 1/2. 1 minus u. 1 minus 2, -1. U squared, 4. Plus c times 1 minus 2 is -1. 1 plus 2 is 3. And then u is 2. Plus d is 1. Times 1 minus 2, -1. 1 plus 2, 3. Okay, so what's going on? 1 equals, that's going to be 6 minus 2 minus 6c minus 3. So I have 1 equals -6c plus 1. So 6c is 0, c is 0. All that just to find out c was 0. I always get mildly upset when that happens. But then I guess it's good. We have less to integrate, right? So we have integral. A was 1/2 over 1 minus u plus b was also 1/2 over 1 plus u. And then d was 1. So that's 1 over u squared, du. From here, integrating's no big deal. Just be careful, when we take antiderivative here, it's going to be ln, absolute value 1 minus u with the minus sign in front of it as well. So minus 1/2 ln, absolute value 1 minus u, plus 1/2 ln, absolute value 1 plus u. And then we can do this in our head. This is u to the -2nd, add 1 to the exponent, divide by the new exponent, so it's minus 1 over u plus c. And then who was u? U was sine theta. So this is going to be -1/2 ln absolute value 1 minus sine theta plus 1/2 ln absolute value 1 plus sine theta minus 1 over sine theta is cosecant theta plus c. Okay, remember though, the problem didn't start in terms of theta. We did a trig sub. So we're going to have to draw a triangle, go back to the original variable. But before we do that, I want to clean up and combine these natural logs just so at the end there's less cleanup to do. This is going to save me a lot of steps down the road. So I can factor out the 1/2 and then rewrite these as a single logarithm, ln absolute value 1 plus sine theta over 1 minus sine theta. And then don't forget, we still have good old minus cosecant theta plus c. Let's multiply top and bottom by the conjugate of the denominator. So I'm multiplying by 1 plus sine theta, top and bottom. And you'll see why things are going to clean up beautifully. And I did this in a recent integral. So we've got 1/2 ln absolute value. This is going to be 1 plus sine theta squared over, now you guys, 1 minus sine theta times 1 plus sine theta, 1 minus sine squared theta. But that's our good friend, cosine squared theta, minus cosecant theta plus c. And then, no, we're not done cleaning up. Take this 1/2, move it, make it the exponent on the argument, and then 2 times 1/2, 2 times 1/2. When I take the square root of something squared, those exponents cancel, so I just have ln absolute value 1 plus sine theta over cosine theta minus cosecant theta plus c. And I'm going to take it one step further. I know, you're like, you're out of control, Professor V. No, I'm not. Because I'm thinking when I make my triangle and I go back from the trig sub, like I'm going to have a fraction here, I might have a fraction here. I'd rather just have this all cleaned up so there's less to do later with the radicals. So this is going to be 1 over cosine theta, that's secant theta, plus sine theta over cosine theta tan theta, minus cosecant theta plus c. Okay, now it's triangle time at long last. Do you even remember what the substitution was that we made? We had let x plus 1 equal tangent theta. So think of that as x plus 1 over 1. Here's your triangle. Here's theta. So tangent's ratio of opposite over adjacent. And then the hypotenuse would be rad x squared plus 2x plus 2. Okay, beautiful. Here we go. So this is going to be natural log, absolute value. Secant theta is ratio of hypotenuse over adjacent. So rad x squared plus 2x plus 2 over 1 I don't need to write. Cool. Aren't you glad we cleaned it up so much? Plus tan theta, that's just x plus 1 over 1, but we don't write that. Minus cosecant theta, that's ratio of hypotenuse over opposite. Radical x squared plus 2x plus 2 over x plus 1 plus c. Very good. So I think that problem was super straightforward, especially if you've been keeping up with the most recent integrals of the day, because we've been playing around with these techniques. So I thought it would be nice to remind you about them and put it all together. How'd you guys do? Did you solve it in an entirely different fashion? I'm sure possible. I'd love to hear about it. So tell me in the comments down below. Thank you guys so much for your support. I have such a good time making these videos. And I will be back sooner than later with more content for you guys. Also follow me on Instagram, TikTok, Twitter, Math with Professor V. Don't forget to give a thumbs up to the video. Subscribe if you haven't already. I don't think I said that yet. Also shop my merch. I have Professor V's Math Police merch, and the design was created by one of my former students. So very special, fun stuff. All right, see you guys soon. Bye.